Howdy. I wanted to do two examples of inclines today. The first one will be a simple example that will not involve friction, and the second will be a slightly more complicated example that will involve friction, but both will be relatively easy. The key point here is the notion of a rotated reference frame. Rotated reference frame. And I want to emphasize that when we rotate our reference frame so that the axes are now parallel and perpendicular to the plane that we are on, then it always turns out that the component of gravity that is parallel to the reference frame has magnitude mg sine theta, where theta is the angle of inclination right here, and the component of gravity that is perpendicular to the reference frame has a magnitude of mg cosine theta. And this is without exception. So please make note of this fact. So our first problem is going to be a fairly simple problem. The skier points downhill on a 30-degree slope. It's a fairly steep slope. It would have what we would call a grade of 50%. And so the question now is, what is the acceleration of the skier? All right, so we're going to draw ourselves a free body diagram. Here we are. Here's the skier, represented as a block. And for this particular problem, I should say, we are going to neglect friction. Skier has well-waxed skis. Okay. So now we draw ourselves a free body diagram, a skier of mass m. Notice that the mass of the skier was not given, and that's okay. We're going to find that it's going to cancel out in the end. And so this is our original mg. The skier is also going to experience a normal force pushing up from the snow. And since we are neglecting friction, there is no frictional force to add, and we are done. Now, the next thing is we're going to rotate our reference frame so that the reference frame lines up both in the direction of the normal force, but also in the direction that we know the acceleration is going to take place. Because we know that the skier is going to accelerate down that slope. And so it makes sense to rotate our reference frame like this. And it also makes a lot of sense to make this direction be the positive direction, and that direction to be the positive direction, because the acceleration is going to be down the slope. So having done all of that, we now take our mg and break it into components. This component will be mg parallel, and this component is going to be mg perpendicular. And mg parallel is always mg is the sine of the angle of inclination, which is this guy right here, which is our 30-degree slope. And mg perpendicular is always mg times the cosine of the angle of inclination. And so now we have all of our forces broken into components along the parallel and perpendicular axes. And we're ready to do sum of forces. Newton's laws. And we're going to do sum of forces in the x direction, which is, in the parallel direction, and we're going to do sum of forces in the perpendicular direction, because those are our axes. In the parallel direction, we have only one force that is operating in the horizontal, the parallel direction, and that is mg parallel. So our sum of forces is equal to mg sine theta. And because we know the skier is accelerating down the slope, therefore that sum of forces is equal to mass times acceleration. We're using Newton's second law. And right here, we notice that if I take the equation mg sine theta equals ma and I divide divide both sides by m, then the masses cancel out. And the acceleration of our skier is going to be g sine theta, no matter how heavy or light the skier is. And punching the numbers in, we have 10 meters per second squared for g, and the sine of 30 degrees is 0.5 exactly. No, I don't know them all, I just know the special angles. And so we get 5.0 meters per second squared is the acceleration of our skier down the slope. So that was a fairly simple example here. Notice that I did not have to do the sum of forces in the perpendicular direction because I was able to solve this first equation for acceleration directly. For our second example, we're going to take a look at a problem from your book, which is number 52. I have it right here. The carton shown in the figure lies on a plane tilted at an angle of 22 degrees to the horizontal with mu k is equal to 0.12. Determine the acceleration of the carton as it slides down the plane, and if the carton starts from rest 9.3 meters up the plane from its base, then what will the carton's speed be when it reaches the bottom of the incline? Notice that 9.3 meters is a very long distance. It's actually, I believe, longer than our classroom. So this is a long, long ramp. Let's go ahead and do our free body diagram. We'll put an inclined plane here. And we'll try to make that inclined plane a little more realistic. So a bit like that. And we'll put our block on the inclined plane. I don't believe the mass is given. Nope. In fact, it gives us a mass of m right here. And so we suspect that the mass is probably going to cancel out, and that's going to turn out to be the case. We'll put our mu k right there, and our angle, which is 22 degrees, right there. And now we're ready for a free body diagram. We have mass m. We have mg going straight down. We have the normal force perpendicular to the plane. And we're going to have a force of friction that is going to be opposite the direction of motion. And since the mass is going down the plane here, the force of friction will be going up the plane over here. All right, having done so, it seems clear that we want a rotated reference frame so that our force of friction, our normal force, and our acceleration will all point along the axis. This is the axis parallel to the plane. This is the axis perpendicular to the plane. And it makes a lot of sense to make these two directions be positive directions. Once we've done this, the only force that needs breaking into components is mg. So we'll scratch it out and replace mg in the parallel direction, matching the axis here, and mg in the perpendicular direction, matching the axis here. And of course, we remember that mg parallel is equal to mg times, yes, sine theta. And mg perpendicular is equal to mg times, yes, cosine theta. So if you need to write these a couple of times just to remind yourself of these facts, then feel free to do so. Now, having done our free body diagram, we're ready for Newton's laws. We're going to sum up the forces in the parallel direction, and we're going to sum up the forces in the perpendicular direction. So we go over to our axes, and we identify, first of all, the forces in the parallel direction, which are mg parallel, which we know is mg sine theta, minus the force of friction. Notice the force of friction is negative because it's going opposite to the direction we said was positive. Now, does the sum of forces add up to 0 or to mass times acceleration? Because the problem, do a quick check here, because the problem is asking for the acceleration of the carton, we have a huge clue that we are looking for Newton's speed, mass times acceleration. Meanwhile, the sum of forces in the perpendicular direction is going to be equal to all of the forces that are operating in the perpendicular axis, which is going to be Fn, pointing up, and mg perpendicular, which is mg cosine theta, pointing down. This sum of forces will be equal to 0 because the carton is not accelerating in a perpendicular direction. There is no component of motion that way. Now, let's see what we can find out. First of all, looking at this equation and solving for Fn, we find out from this equation that Fn is equal to mg times the cosine theta right here. It bothers us a little bit, just a slight bit, that they don't give us too many numbers. But we have become experienced enough to be able to handle that. At this point, we can substitute numbers in, or we can leave it as algebraic. I prefer to leave it as algebraic, but if you want to substitute numbers in at this point, just to kind of keep your head straight, then that'd be okay. So, bear with me. I look at these two equations, and what I'm looking for is the acceleration right here. And I look and I see that I have the following variables. I have Fk, I have acceleration, the sine theta, the theta is given to me, so that's a constant. The g is given to me, and I figure m is probably going to cancel out because it usually does in these problems. And finally, I have the value of Fn right here. So it seems to me that I need a little bit more to be able to solve. I need one more equation to be able to solve, and that equation is the friction relation. Fk is equal to mu k times the normal force. And the value of mu k is already given to me, so I can substitute what I know the normal force to be. Now that I have the frictional force, I can substitute that into this equation right here, and I can find that mg sine theta minus mu k mg cosine theta is equal to ma. And again, I could have plugged in all the numbers that have been given to me. I know g, of course, I know sine theta, I know mu k, cosine theta, I know all those things. But I wanted to leave this in symbolic form so that you can see the form of the answer. We notice that mass is a common factor on each side, so that if I divide through by mass, it all cancels out, and I get the acceleration, which is equal to g sine theta minus mu g cosine theta. Let's actually get a number for that at this point by plugging in for g. 10 times the sine of 22 degrees. You're going to have to ask your calculator what that one is. It's going to be a little bit less than the sine of it's going to be a little bit less than the sine of 30 degrees. And I get 0.375 for that. Minus mu k was, I believe, 0.12. Let's check the problem. Yes, mu k is 0.12. And the cosine of 22 degrees, according to the calculator, is 0.927. Just like that. And all of that then, when you multiply it out and subtract, is 3.75 minus 1.11, which gives me 2.64 meters per second squared as the acceleration. Let me just check my numbers on that. Something's bothering me. Yeah, I know what's bothering me. This should be smaller than 1.11 because, no, it shouldn't. Looks about right. Let me just double check. Nope, that's correct. Okay, good. And so our acceleration is 2.64 meters per second squared. That's part A. Part B is much more simple. To review what we did here, the key was Newton's laws that gave us equations that we could solve, and we needed the friction relation as our third equation. Once we had that, the algebra kicks in, and we solve by substituting. In part B, they ask us if the carton starts from rest 9.3 meters up the plane, what will the carton's speed be when it reaches the bottom of the incline? Well, let's go through and label quantities like we do. Starts from rest means that v0 is equal to 0. If it is going to travel 9.3 meters, then that means that its delta x is equal to 9.30 meters. And we are looking for the carton's speed, which is the final v right there. Well, this suggests to us that we want to use the equation v squared equals vo squared plus 2a delta x. What might bother us, though, is that this equation we use for motion along a line. And so is that really appropriate here? Well, actually it is, because this carton is moving along this line right here. And since I know the acceleration along this line, and I know the delta x along this line, then if I allow the carton to move from rest all the way down to here, then I will be able to find the final speed, which is appropriate in this direction. So yes, this is the right equation to use, and we have an initial velocity of 0, we have the acceleration captured from the first part, and we have the distance 9.30 meters. And so punching the numbers in gives us that v squared is equal to 2 times 2.64 times 9.30 is 49.1 meters squared per second squared, and therefore v is equal to 7.01 meters per second. And there you go. Well, I hope this was helpful to you, and I will see you